Welcome to part 2 in the overview of pattern relationships. In part 1 of this series, we motivated the need for pattern relationships that go above and beyond traditional pattern collections. And we also outlined the most common types of pattern relationships that you'll find in the literature. In this part, we're going to describe some of the key concurrent and network software patterns associated with the domain of avionics control systems. An avionics control system continuously collects sensor data to estimate the actual state of an aircraft. It computes the desired aircraft state with respect to the various guidance modes it's in. For example, is it in autopilot mode? Is it in terrain following mode? Is it in waypoint navigation mode, etc.? And then the control system performs various actions to advise the pilot or pilots or to directly manipulate the aircraft effectors, the ailerons, the control surfaces, and so on the wings and the tail and so on, in ways that bring the actual and desired states closer together. Some of the common functions you find in an avionics control system would include things like the heads-up display that provides easy accessible information to pilots to avoid distracting them by having to look down at their cockpit dashboard. Things like autopilot, which are used to navigate the plane between waypoints automatically, and a whole other variety of different sensors that collect information about where the airplane is and what is going on around it. Now, it turns out that I've worked on these kinds of systems for a long time, as have others. And there's a real nice description of domain patterns for avionics control systems that you can find at this website by my colleague Doug Lee, who's also, of course, famous for his work on concurrency and Java programming and other contributions to distributed systems, middleware, and object-oriented programming design and implementation. The particular projects I work on go back to the mid-90s, and I worked on these projects for about 8 years or so. And what we were doing is we were taking existing legacy systems and trying to update them to use more modern design approaches. So I'll be describing a number of patterns that arose in the experience we gained on this system in order to help motivate the key points relating to patterns and how we can combine patterns together in various related ways. If you take a look at the URL at the bottom of this slide, you'll find many, many papers that describe all kinds of aspects about the systems we were developing, the middleware, the patterns, and so on. You don't have to be an expert on avionics control systems to make sense of what we're about to talk about, but let me give you a little bit of background to help motivate why we're looking at patterns and why we're trying to solve particular sets of problems in this domain. So some of the key domain characteristics of an avionics control system are the following. They typically have a number of hard and soft real-time deadlines, things that either must get done or the airplane starts to spiral out of control, or we'd like to have them done in order for the airplane and the pilot to do a more effective job of their mission, which could be getting the passengers to their destination safely and fuel efficiently, or putting out forest fires, or surveying a certain area to look for survivors after some kind of disaster, etc. Typically, these deadlines tend to run within what's called frames. Every 50 milliseconds or 25 milliseconds or so, a bunch of input has to be received from sensors and processed in order to be able to update the various state and to control the actuators on the plane in sensible ways. Not surprisingly, as we do more and more complicated things with airplanes, we start to include multiple processor boards. And it's important for communication between these boards to be very low latency and be very predictable. We don't want to have high overhead. We don't want to have a lot of variation, because that makes it much more difficult to be able to build systems that will be schedulable and able to be certified to be mission and safety critical. A lot of the processing in these systems is periodic, driven by the rate at which sensors are polled or pushed for the data that they provide. There also is other kinds of aperiodic processing, things like built-in test that runs as time and cycles permit in order to make sure that the integrity of the software and hardware is as expected. There are also a number of complex dependencies in these systems. One of the classic dependencies is that the software and hardware is often co-developed, and the software is tightly coupled to particular characteristics of the hardware. And you can imagine, of course, some of the consequences of these dependencies is that it's very difficult to upgrade the software and the hardware over time. Some of the projects I've worked on in the early days would take 5 years or so to be able to certify changes to the software. So by the time someone actually went ahead and purchased an airplane, to 4 or 5 years later when the plane rolled off the assembly line, there could be literally no changes made to the functionality or the operating system or the hardware or the programming techniques and so on. And you can imagine that's very expensive and costly to do. Avionic control systems are representative of a whole class of distributed real-time and embedded systems that require robust concurrency and networking support in order to be able to meet their mission goals and requirements. Often these systems are characterized as ones where the right answer delivered too late becomes the wrong answer. Historically, people have built these kinds of systems in a very brittle and stovepipe manner. They would typically take some pieces of hardware that were very specialized and customized, build specialized control systems using things called cyclic executives, which are basically very simple operating systems that run through a set of functions in a particular order, in a particular time sequence, carrying out certain operations. And these operations are often very tightly coupled. They tend to access shared global data. They tend to be written as functions, often written in low-level languages or unusual languages like jovial, which very few people know these days, which makes them expensive, and it also makes them vulnerable because it means that if you start trying to connect these things together across a network, you may not understand some of the secure coding problems because people built these systems to run as enclaves, not to be connected together. Some of the problems we're going to talk about and focus on the application of patterns for relate to issues associated with tight coupling, making things hard to schedule, making them brittle and expensive to change. And we'll be talking about ways in which patterns can help to break these couplings in ways that make the system easier to evolve and maintain over time. And that was really the driving force of the systems I worked on in the late 90s that you can read more about at these URLs. To describe the patterns, we're going to use an abbreviated form of pattern description known as a patlet. We're not going to do the full-blown pattern descriptions that we've done in some of our other slides, but instead we're going to focus on some of the key characteristics. What's the context? What are the problems? Outline the solution, and then show how we can apply the solution in the context of our case study of avionics control systems. So let's start by talking about some of the problems we ran into. When I first started working on this project, historically these systems were developed in a very, very tightly coupled way. People wrote them in assembly code or C or these other unusual languages like jovial or in Ada. And they were very complicated. It was hard to make any changes. It was hard to make changes because the minute you made changes, it tended to break some of the assumptions about timing, which meant that the systems were difficult to certify and schedule. And all of this meant that it was extremely expensive to try to build and evolve the system. When I first started working on the project, I had been a reviewer for the POSA 1 book, in addition to having been a reviewer for the Gang of 4 book a couple years before. And I had read about something called the publisher-subscriber pattern, which appeared in the POSA 1 book. And we applied the publisher-subscriber pattern to our avionics control system in order to decouple the publishers that periodically generated I/O-driven data from the sensors and delivered them to the consumers that processed this data in all kinds of different ways. Now, it turns out that that particular pattern is responsible for disseminating events or data between various publishers and subscribers in a way that allows the subscribers to receive the events that they've registered their interest in and allows the implementation of the pattern to be selective in how it disseminates that information and decoupled, most importantly of all. The structure of this pattern has a number of canonical roles. It typically has something called an event channel, which is basically a mediator that sits between the publishers and subscribers. When the subscribers register themselves or attach themselves to the event channel, they indicate the types of events that they're interested in, and the event channel then makes sure to disseminate those events only to interested subscribers. You can take a look at the URL at the bottom of the slide for more information on the publisher-subscriber pattern, and of course you can also take a look at a much more detailed description in the POSA 1 book. The dynamic relationships in this pattern are as follows. Subscribers will come along and attach themselves to the event channel, indicating what event types they're interested in. And when the publishers produce the events, they go to the channel, and the channel is responsible for disseminating them on to the subscribers that have indicated an interest in that particular type or types of events. If you take a close look at this pattern, you'll very quickly notice it looks an awful lot like the observer pattern from the Gang of Four book. And in fact, they share many things in common. They both involve notifying some number of observers or subscribers when something of interest happens. In the case of observer, it's typically when some change takes place to state. Observer is typically thought of as a change propagation notification style pattern. Publisher-subscriber, in contrast, is often used to do event dissemination, which may or may not necessarily relate to changes in anything. It may just be the next chunk of data has arrived, or you have something you want to communicate out to various interested parties. Another way in which those patterns differ to some extent is publisher-subscriber is much more explicit about the need to be able to register filters for the subscribers so they only receive events that they're interested in. When we applied publisher-subscriber to the avionics control system we worked on in the mid-90s, we started by refactoring the existing software, which at the time ran on a single processor board. And we took the existing code and we rearranged it, we refactored, re-engineered it, so we had publishers that were associated with the incoming sensor data. We had an event channel that was responsible for queuing up the data and then disseminating the data out to the appropriate consumers. So we didn't actually have to write a lot of new code. We just rearranged what we had to more closely correspond to this pattern instead of being driven in a very highly coupled way by a cyclic executive. Some things that we had as a benefit of doing this are as follows. We were able to have much better anonymous communication between publishers and subscribers. They didn't have to know about each other. They were less coupled, which made it easier to evolve and add new consumers and new publishers. We also were able to provide group communication. Not all consumers, not all subscribers wanted all the information. Sometimes there was one subscriber that wanted it. Sometimes there was a group of them. And we could do the one-to-many mapping very easily using various filtering mechanisms we implemented. The other nice thing about our design was it allowed for asynchrony. You didn't have to wait. When a publisher published an event, it didn't have to block waiting for the consumers to read it. And that allowed us to simplify our threading model. It allowed us to be able to provide various other kinds of benefits to decouple the system and make it less brittle and hard to evolve over time. There were, of course, some implementation considerations, some of which were documented in the pattern, some of which we had to learn through the School of Hard Knocks in those days. Some things we had to worry about had to do with whether we used a push model to push control and data from the publishers to the subscribers, or whether we would push control and then pull the data. And it turns out that there's a whole variety of different trade-offs between these different approaches, some of which are described in the papers available on my website. We also spent a lot of time worrying about how to schedule incoming events in the event channel. We played around with different models based on priority-based dispatching, first in, first out, or FIFO dispatching, with the goal of trying to make sure that the high priority consumers receive the data before the less high priority ones in order to ensure our deadlines were met. And of course, we also spent a lot of time wrestling with different ways to efficiently implement event filtering and correlation so only the consumers that really needed the data would receive them. And by the time we were done, we'd written a lot of code. we were able to successfully test fly our solution, and it worked nicely for the original prototype requirements we'd been given by our sponsors. But of course, as luck would have it, as soon as we'd succeeded with the prototype, people came back and said, hey, that's great. Let's go ahead and add a lot more functionality to be closer to the real system. Well, we were stuck. Our original design had used publisher-subscriber, but it didn't have a way to communicate from different processor boards. And when we started to look into this, we realized that there was going to be a lot of need to talk across these processor boards in order to scale up the functionality properly, given the CPU resources we had at our disposal. The solution we had to come up with, of course, also had to meet various quality of service requirements. It had to be predictable. It had to be fault tolerant. We didn't worry too much about security in those days, but nowadays we'd worry a lot about security. And most of all, we wanted to make sure that we could shield the application developers, who were not experts at object-oriented software or middleware, from the complexities of the networking and concurrency. We didn't want them to have to wrestle with low-level message passing using sockets. We didn't want them to have to worry about different programming languages or operating systems. We didn't want them to have to worry about partial failure, latency, and so on. So what we did is we applied another pattern from the POSA 1 book, this one called the broker pattern. And we used that to isolate the applications in the avionics control system from all the underlying communication concerns that were required to pass the information across the different processor boards. At the same time, I'd also had been learning about CORBA, the Common Object Request Broker architecture, and so we felt that the combination of the broker pattern plus the CORBA standard would provide a good infrastructure for building a solution that would meet our needs. The broker pattern connects clients with remote objects by mediating invocations from the clients to these objects while encapsulating all the low-level communication concerns: the connection management, data transfer, memory management, concurrency, synchronization, fault tolerance, demultiplexing, you name it. What you typically do is you have a client make an invocation on a proxy. That proxy then uses the broker implementation to deliver the message corresponding to that method invocation across to the other address space, where it's received and reconstituted back into a method call on the remote object. And of course, you can have two-way communication and one-way communication and so on. Here's a diagram that just illustrates these dynamic steps. The application server registers its objects with the broker. The client discovers those through various means, like a naming service. And then it goes ahead and invokes the operation through some kind of object reference. And the proxy and the adapters and the broker implementation does all the heavy lifting to shield the application developers from these low-level details. Well, we turned around and implemented the broker pattern using CORBA as the guiding design interface and put together a real nice open source implementation called the ACE Orb. And we're able to retrofit our existing prototype that was a single board solution to make it work predictably and efficiently in a multi-board solution. And one of the nice things about providing a broker was it shielded the application developers from all the diversity in the underlying infrastructure. We could have people writing parts of the system in Ada, or C, or C++, or, as came later, real-time Java. And the broker took care of all those low-level details. Likewise, the choice of operating system became an implementation configuration decision. The choice of hardware, the choice of the communication protocols, all those things were no longer the application developer's responsibility. The broker implementation took care of it. Well, of course, as before, the pattern got us part of the way. The patterns in those days really hadn't thought through all the implications for quality of service. So there were various issues of real-time scheduling, real-time delivery of data, demultiplexing, making sure that you minimized variation in latency called jitter, making sure you maintain priority end-to-end to avoid priority inversions where low priority tasks block high priority tasks and so on. And of course, we also had to deal with other illities, dependability, securability or security, and other factors. And throughout this process, we not only had a better understanding of how broker worked, but we also documented a lot more patterns. One of the things you should see at this point is that the use of the broker in conjunction with the publisher-subscriber underscored the earlier point I made that patterns aren't islands. They work together. They're involved. In our case, we use the broker underneath the publisher-subscriber in order to make it work across different address spaces. Of course, it's also possible to implement publisher-subscribers that don't use brokers at all. Things like the OMG Data Distribution Service, or DDS, is a good example of a publisher-subscriber abstraction that doesn't use a broker under its innards to do the dissemination of the information. What we're going to do in the rest of this part, very briefly, is summarize some of the other patterns that are commonly used when developing brokers. We're going to focus on Corba right now, just because that's what we did when we built the system, and it's a nice starting point. But be aware, as we get further along in this course, we're going to be exploring other uses of these patterns in ways having nothing to do with Corba. And we'll also be looking at some of these patterns in more detail than we're going to give you right now. This particular discussion can be found in a paper we wrote a number of years ago, as well as in Chapter 6 of the POSA 4 book. So here are those patterns real quick. So one pattern we apply to implement broker is the layers pattern, which is a POSA 1 pattern that talks about how to structure software to separate concerns in a layered manner. And of course, we use this throughout the broker to be able to decouple the operating system layer from the layer that's dealing with some of the basic request processing, from the layer that deals with turning request messages back into method calls on objects and so on. We also apply the wrapper facade pattern. Wrapper facade is a POSA 2 pattern that makes it easy to enforce portability by providing a layer that abstracts away from low-level operating system details to make software easier to move between operating systems. We apply a couple of Gang of 4 patterns, the proxy and adapter pattern, which make it easy to separate the application logic, which is method-oriented, from the underlying broker, which is message-oriented. We apply something from POSA 2 called component configurator, which makes it possible to dynamically configure factories, which is a Gang of 4 pattern. And we have these factories create strategies, which is another Gang of 4 pattern. And these strategies are then used to implement various broker mechanisms for concurrency, synchronization, multiplexing, demultiplexing, marshalling and demarshalling, and so on. Some of the concurrency strategies we would use might be reactor and half-sync, half-async, or leader followers, which are POSA 2 patterns. We can also use a POSA 2 pattern called monitor object to synchronize concurrent access to objects. And we're going to use the acceptor connector pattern to decouple connection management and service initialization from the application protocol or broker protocol used to communicate information once various parts are connected. Now, I've gone through these patterns at a very quick clip, and I've given you some URLs you can use to learn more about these patterns. To really get a deeper understanding, I recommend you take a look at the POSA 1, POSA 2, and Gang of 4 book. So to wrap up this section, patterns help to overcome limitations with traditional avionics mission computing system architectures and control system architectures. Of course, they also help to solve problems in other domains as well, other concurrent and network software. We apply these patterns very effectively to move away from a very brittle and tightly coupled and hard to schedule, hard to evolve, costly avionics control system solution to come up with one that was much more modular, much easier to understand, much easier to maintain. In the rest of this particular module, we'll explore other relationships between the patterns we've covered so far, as well as other patterns that occur in this particular space.